Well, hi, everybody, and welcome to this session. It's a pleasure to be here. My name is Javier de la Torre, and I'm the founder of Carto, which I will talk later. And I'm here with me, James. So, James.
Hi, yeah. So I'm James Bentley, and I'm a data scientist in our market information group, which I will explain what we do in a moment. So first, we're going to go through a bit of a journey that we've been on in optimizing some of our geospatial pipelines, and then I'll hand back over to Javier, and he can go through Carto and the amazing things that that can do.
But sorry, I mean, like maybe before we get even started, how many people here are used to geospatial data and knows about things about geo? Oh, fantastic. Okay, great. So we can go straight to the meat directly. Okay.
Brilliant. It's always good to see so many people interested in geospatial data. I think especially at a conference so heavily dominated by things like AI, it's often a field that gets a little bit forgotten. So yeah, as I said, I'm James Bentley. I'm a data scientist at Landmark Information Group, and we're the UK's largest provider of property data. We provide all sorts of services from sort of risk management and especially around climate change risk, and also services such as property valuation. So if you've ever bought a house in the UK or insured a house in the UK, it's very likely that you've touched our services at some point, knowingly or not. Internal to Landmark, I'm part of the innovation team. So we do all sorts of things from deriving insights from new and existing data sources, using tools like generative AI to make new products, both internally and externally. And what I'll be talking to you about today is we also work with optimizing and looking into processes that we already have internally and seeing how we can make them better. And the one that I'm going to be focusing on is called GeoCat, or the Geospatial Catalog. Now, this is a POC, a pilot project, which, as all good POCs do started completely by accident and now is gathering quite a lot of momentum quite quickly. And it's how we've been trying to index all of our internal data sets against a common index so that they can all talk to each other. And it started basically with a basic question of how far is this from the coast? Now, this is a really important question for us. Distance to the coast is an impacting factor for all sorts of risks, such as flood, coastal erosion, but it also comes into things like property value. Properties nearer the coastline can tend to have higher value, especially if they're in nice areas. And the way that we used to find this is we would take all the properties in the UK, and we would take a vector line string of the coastline, which is where sort of the average high water mark for where the tide comes up to. Except the coastline for the UK is actually really long, and that would be one massive line string. So it's actually broken down into a series of smaller line strings. And the way that we used to calculate this is we would take all 40-odd million properties in the UK, all these thousands of small line strings, do a big cross-join, calculate the distance, and then take the minimum for each one. And then we have how far each individual property, that specific point is from the coast. Now, as you can imagine, this scales horribly, and it's very inflexible for reasons that we'll see in a moment. So we were given this and we were told, well, can we make it any better? Can we speed it up? And after a bit of research, we landed on using H3 indexing. Now, why H3? It's got a series of benefits. I'm sure a lot of you are already quite familiar with it. The first main benefit is that we have endless universal traversal. So this means that the whole world is covered by hexagons as big as over 1,000 kilometers in edge length, all the way down to about 50 centimeters in edge length, and sort of everything in between. And that covers every part of the globe, so it's completely universal. Hexagons tessellate perfectly, which means that all the neighboring hexagons are always the same distance from the core hexagon, and that makes things like calculating distances very efficient, because the third benefit, root 3, is a magic number. So if you have the edge length, which is easy to find for all the hexagons, you can use root 3 to find the circumradius, and from that you can multiply by how many hexagons one cell is from another, and then you have a very rough estimate for how far away those two hexagons are in terms of meters or your unit of choice. So you can very quickly start to do very efficient calculations, but also each H3 ID index has its own ID. So each H3 hexagon you can uniquely identify in a tabular format. So how did we apply this to the coastline? Well, we took a part of the coastline geometry, and we found the H3 cells that go along that line. So those are 0 distance from the coastline. That is the coastline for those H3 cells. We then did K-ring buffering, so essentially adding a layer of hexagons all the way on the outside, and then making a note that that is a distance of 1, distance of 2, 3, 4, and all the way up. So this grew quite nicely and made this very pretty looking map. But it's color-coded so you can see how far each H3 cell is from the coastline. And that allowed us to have a map that looks a bit like this. So the deeper blues are, as I said, on the coast. And the more sort of like yellowy colors as you get towards the edge, that's getting to a grid distance of around 8 or 9. So 9 cells away from the coastline. In a tabular format, it looks like this. So each cell, as I said, has its own unique ID, which can be expressed numerically. The grid distance of how many H3 cells it is away, and the ACG IDs. This was a feature which I sort of just put in and then very quickly became a core feature of the POC, so I can't really get rid of it now. But it's an array of surrogate keys for which original piece of coastal geometry that hexagon is nearest to. And that allows us to do either a grid distance calculation, which is, well, it's not even really a calculation, it's just there, and we can know how far that cell is from the coast approximately, or we can join using that surrogate key and do a single distance calculation to know exactly how far away it is. So zooming in, it looks like this. As you can see on the old method, there's all the individual properties with the coastline, and in the new method, each property is assigned to an H3 cell. And this comes with numerous benefits, 4 main ones that I'm going to go through. The first is general indexes enable arbitrary searches. So what do I mean by that? Well, take, for example, this scenario, and then say that someone come along and wants to ask, what is the risk of building a house here? How far is it going to be from the coastline? In the old method, we would have to do, well, exactly what we always did. We would take that point and cross-join it onto all the line string geometry, find the minimum distance, or we'd have to do some sort of aggregation of the nearest by points. Either way, not really ideal. In the new method, that H3 cell already exists. We already know roughly how far it is from the coast, and if it's beyond a certain point from the coast, we can just immediately say, oh, it doesn't matter. And if the grid distance is low enough, then we only have to do a single calculation to find out how far that is from the coastline. And it doesn't just have to be distance to coast. It can be all sorts. For example, this may look a bit like a raster, but this is actually a series of H3 cells. And this is representing temperature data and predicted heat waves throughout the UK. And if we look under the hood, exact same sort of thing. So the same H3 indexing system, the name of the county where that point is for, and then sort of the maximum temperature predicted for that series of days and the heat wave threshold. So something that would previously be stored in something like a raster can now be stored tabularly. And this kind of leads me to my second benefit, which is we have reduced computational requirements when using H3. So what do I mean by that? Well, obviously, as I said previously, this was a really horribly scaling system which took 10 days to run and had no flexibility because all the points were assigned to a single geo point. With the new system, however, most of our cells only have one nearest by line string, so we know exactly which distance we need to calculate if we're looking for precise distances. Some have 2, but 97% of cells have no more than 2 nearest by line string geometries. And most of the ones that do have more than 2 are up on the coast of Scotland, where the coastline is incredibly complex and the line strings are actually very short in real terms. So that allows us to take our previous 10-day process, which was using sort of just standard SQL, and now it runs in about 2.5 hours and gives us full flexibility of how we consume it on the other end. That 2.5 hours is running about 10 Databricks units per hour. So about 20 Databricks units, so I think that's about $10 at the moment, or £10. Yeah, so a massive improvement. But that's just that's just an improvement in generating. What about consuming? Well, for that, I want to take a quick detour and talk about electricity pylons. They're not very pretty, but we are very interested in them because they have quite a devaluing impact. Visual safety. You can't do as much with your property if you live nearby to one. And when it comes to pylons, distance matters, but not precisely. So we care if you're within a a radius of one, but we don't care if it's 1 meter or 50 meters. So say, for example, we have a pylon here, and we have a radius of 100 meters. Now, previously, again, we'd have to do some sort of horrible cross-join and find, is this property near any of the pylons in the whole of the UK? Or even if we did some sort of intersection of a buffer, you're still checking against every single pylon. Does this property intersect with it, yes or no? The method that we decided to go with in speeding up our consumption of this is a library called Databricks Mosaic. And this uses H3 and indexing at its core, but it has a couple of tricks up its sleeve. So you can see here, I've drawn a 100-meter buffer around this pylon, and that H3 cell in the center, that's more kind of yellow. It would have been better if I remembered my laser pointer, but oh well. The more sort of yellowy cell, that is a core cell. So if we have a property and we want to know, is this property within a 100-meter buffer, we can get the H3 cell ID for that point. We can take this cell, and we can ask, is this core? And what that basically means is this cell entirely enveloped by the polygon geometry that we've drawn? And in this case, we can see that yes, it is, so it is core, and that's all we need to do. We get the H3 cell, cell ID for this property, we left join it onto this H3 cell from the buffer, and we just do a single Boolean check. Is core true? Great, okay, so we don't need to know any further. We know it's within that area, we know it's within 100 meters, doesn't matter where within the cell it is, all good, we can move on. So then, say for example, we take this property. Well, okay, we'll do the same thing. We'll get the H3 cell for this new property. We'll left join onto the H3 cell from the buffer, and we can see that in this case, it is not core. So you can see that the yellow highlight there is only on the left, a bit of the buffer, and because it's not fully enveloped, that is not a core cell. So we do the same. We left join, we check, oh, false, it's not core. So we need to do one more thing. We do a single intersect calculation with the well-known byte geometry from this chip, so like this bit of the cell. So you can see it's like a funny looking bit on the left. And this way we only have to do one single targeted intersect calculation. In this case, it comes back false, they don't intersect, so we can move on and we can say that this property is not in fact in the 100-meter buffer. And we can sense check that, and yes, it works. And obviously, this is, looks quite simple on this level, but when you scale it up to millions of properties and thousands and thousands of pylons, it really does speed up the process quite considerably. But it doesn't just have to be for these sort of proximity calculations. It can be for any sort of geofencing applications. So I have thousands of vehicles in this fleet. Are any of them within this area? Or a customer is right here, which of our millions of shops or stores that we have on record are within a X meter radius from this person. And it can also be done to respect border geometry. So quickly going back to this heat stress data set which I showed earlier, the bit I didn't show you at the time is these two columns on the left, which is core and chip. So this allows us to take data, rather than assigning it to every single property and repeating data loads of times, because this doesn't really change much over the local scale, and having millions of rows, we just have one row per H3 cell, and we can know which county it's in, check if it's true, and if it's not true, for example, row 5 there with Kent, we get the well-known bytes for the bit of the county border that we are intersecting with. And that looks like this, which I also find very pleasing to look at. I just really like the lines. But yeah, you can see that some of these cells are core, they're fine, they're definitely within that county, we don't have to worry about it. But then some of them aren't, so then we just have to do that single intersect calculation to see which side of the county border we're on, which again really speeds up the consumption of this as well as the generation. So this leads me to my third benefit as well, which is that using H3 indexing, we can have unification of different data sets to aid in our consumption of them. So this is a sort of sample data of retail areas that we got from the Carto Data Observatory. And we can take here all of our different data sets which we've started to put into this indexing system. We've got DTC, distance to coast, wind turbines, pylons, subsidence risk scores. And previously, we'd have to get the point for an individual property or the polygon geometry and then try and join them all using intersects and things like that. Now we can just join on H3, and it's much simpler. any sort of complex joins and cross joins and things like that are now just reduced down to single left joins of different tables. So it's essentially using this as like a master key to join together all these different data sets. And you can just keep on going like this. If all of your data sets have an H3 ID, you can just copy and paste left join, whatever it is, on H3, and you're good to go. And if you do need to consider sort of like, as we said, things like borders, then you can start doing additional Boolean checks quite simply. But unfortunately, because we're British, we do have our BNG local grid, and we very much insist on using it all the time, which is a little bit complex. Just a little bit of complexity to make it more fun. So we do have other ways that we index things. So traditionally, we've always used the UPRN, which is the unique property reference number, basically an ID for every property in the UK. And some things do have to be at the point level. You know, we like address, EPC, sale history. Sorry, EPC is energy performance certificate, how efficient your house is. Those things can't be aggregated. They have to be at the point level. Then we've got H3, as we've discussed, brilliant for things like distances, aggregations, neighboring data, all that sort of stuff, especially because, as we said, those hexagons tile so nicely and the neighbors work so well together. So H3 is brilliant for that sort of thing. And then we do get a lot of native data sets from Ordnance Survey and sources like that, which always use BNG. And it is quite useful in the fact that, you know, it natively uses meters, which make some calculations a bit more intuitive to read and report. And converting between them can sometimes result in inaccuracies, especially towards the outer edges of the UK. We can get drift of sort of up to 5 meters. Which doesn't sound like a lot, but if you're finding if a house is within 10 meters of a tree, that's a 50% margin of error, which isn't brilliant. Luckily, however, Databricks Mosaic is incredibly flexible and tolerant of this, and we can work within that ecosystem quite nicely. So we have addresses and UPRNs at the top there. We can, luckily, each UPRN comes with both its latitude, longitude, and its British National Grid, eastings and northings, which allows us to convert between them and H3 and BNG very easily. And then, yes, using Databricks Mosaic and tessellating to hexagons or BNG squares, we can then go between the H3 and the BNG and geometry. We are also working on a way of converting directly between H3 and British National Grid, which is proven to be a little bit more tricky, but we've got some ways where we can get that down from error margins of around 5 meters at the peripheries of the UK down to about 0.5 meter. And that's using a tool called Grid Inquest, which Ordnance Survey make and allows for a bit longer, but far more accurate conversions. And using UDFs on Spark, we're able to implement them actually quite rapidly, and it's proven to be quite successful so far. So just touching on some of our other data sets. Obviously, I know I focused a lot on particularly distance to coast and things like the pylons, but we've started to involve loads of our data sets. We have hundreds of internal data sets, all coming from different sources, different formats. You know, we've got vector, we've got raster. All the rasters have different formats. All the vectors have different coordinate reference systems. It's a nightmare. And we also have them, as I said, for all sorts of different purposes. Things from just value modeling down there at the bottom and risk modeling at the top. So I've sort of done a crude compass here. As I said, this is just some of the data sets that we've been able to include, but it's really been able to allow us to take the pressure off relying solely on rasters, which we would traditionally do for things like flood risk and subsidence, and also to find new connections between data sets which we wouldn't otherwise have previously put together. Things like, you know, land value and landfill. Traditionally, they've been in very different corners of what we do, but because they are now all talking the same language, we can start to have a look at, well, how does proximity to landfill affect land value and vice versa? And just one that I want to quickly comment on in the bottom right there, solar potential. This was a project where we were looking at the angle and direction that all the roofs face in the UK. And traditionally, you would probably store that sort of thing either at the UPRN level, just tag a house and say this is how many square meters it has of roof facing this direction at this angle, or you'd have a raster. In this case, that is actually neither of those. That is just British National Grid grid references. So that is fully tabular. That's not a raster at all. You can just look up any square meter in the UK, which will have its own ID. And you can find out if it's null. Obviously, there's not a house there. But if there is, you know that there is a house there, and you know which direction the roof is facing, and you know the angle. So again, it allows us to sort of quite quickly start doing polygon searches using data that we already have available, rather than trying to mash these different data sources into bespoke data flows. And finally, I just want to go through the fourth benefit before I hand over to Javier. So using our H3 indexing has allowed us for better visualizations for improved stakeholder engagement. So I've been showing this one a lot. It's because I really like it, and all the stakeholders really like it because it looks pretty. But this was made in Carto, which has native H3 support, which means that we can run our pipeline, save it out into data. We can do Z ordering on the H3 cells as well, which allows us to really significantly improve the read efficiency and memory efficiency of storing this data. And then Carto can plug directly into our Databricks Lakehouse and just read the data and load it into a map. I have been in a meeting specifically where we were trying to decide where some of the bits of the coastline actually stop around some of the rivers and estuaries, where there was a lot of back and forth about, should this be it, should this be it? And whilst we were in that meeting, someone suggested a change. I was able to implement it in Databricks, run the notebook for a small sample area, so it only took about 2 minutes to run, save it out into Lakehouse, and within about 6-7 minutes of this person suggesting it, it was already reflected in the Carto map. And so it allowed us to have like these really dynamic back and forth discussions about how we're defining things and making sure that everyone is happy with it and on the same page. But it's not just stakeholder engagement, it's also external. So previously, we would report a lot of our data, and especially risk reports and things like static PDFs and static images. But some of our clients have over 1 million properties in the UK that they want to know the risk for. So if you provide them a traditional PNG, which is about 10 by 10 centimeters in the PDF, is basically meaningless. It's just a series of dots. Whereas using H3 and things like Carto allow us to have more interactive maps where people can actually pan around, they can understand the data, they can zoom in, they can zoom out, and it all aggregates quite nicely. So it immediately makes more sense to look at. And allows us to modernize a lot of our reporting as well. As I said, rather than sort of static PDFs, we can now have dashboards and iframes with Carto maps embedded. And going back to those really simple SQL queries earlier, we can update them really rapidly. If a customer wants another feature in their map, we can give that control over so that we can start adding different metrics to our maps. And this is just if it loads, there we go. A little demo video of what it's like just to zoom into one of these maps. As you can see, the H3 cells dynamically shrink down, and that allows you to really drill down into problem areas and gives our stakeholders a lot more control. And then that combined with things like widgets, sliders, all the things that you traditionally get in other BI tools like Power BI. That allows us to give the power of understanding and analyzing and interpreting this data a lot more into our clients' hands. So yeah, using H3 has really allowed us to leverage Carto fully, especially as Databricks makes more advances around H3 and geospatial data types and everything. And Carto then enhances how Databricks can be used, and the synergy just sort of like keeps picking up. I promised myself I wouldn't say synergy at a conference. I've just broken that. Oh well. But yeah, on that note, I will hand over to Javier, and he can tell you more about the wonderful things that Carto can do.
Thank you, James. So I think that was a great love letter to H3. How many people know here what use or know about H3 already? Okay, great. Oh, well, it's a lot. So, and that's great because for me, I mean, like this is one of the biggest advantages when it comes, to have a geospatial analytics at a scale. Like really, H3 or spatial indexes are like really a fundamental block to kind of like do scalable data pipelines. So actually, I'll show it later, but for those, I mean, I hope like you all know, but H3 functions are natively supported already in Databricks. So you can use it, and they're like really fast, they're photon accelerated, and they're like, it's pretty amazing to use H3 within Databricks. Now, I want to tell you a little bit about Carto and a little bit of some advances that are happening on the geospatial support on the Databricks and the Spark ecosystem, which I think have been very relevant. And if we have time, we might even do a little bit of a demo. So not going to explain too much. We have a booth if you want to have a full demo later, but Carto is a spatial analytics platform. So it allows to make all the maps that James was showing before, and also many more things. So one of the things that you can do with Carto is that a lot of these spatial analysis, you can do them visually on this type of interface, and that creates workflows, like Databricks workflows, and that compiles into code that then executes by Databricks. So essentially kind of like trying to make easier spatial analytics to users. You've seen a lot of demos already from James around visualization. So we provide you with tools to visualize, especially very large data sets, also small data sets. But if you have like millions, sounds like a lot, but like if you got like billions of records or like very large rasters and so on, we can help you in that. And finally, a lot of the things that you've seen and that we can show you, like you can integrate them into your own applications through our APIs and SDKs. So it's a lot of our users use us that way. Now, I like to say, like this one, I'm sure here there's a lot of like a mix. I like to say that everything happens somewhere. So this really applies to almost every industry that you can think of. So so we work in a lot of industries. Now, before talking more about Carto, also a little bit about like support of Geo on the Databricks ecosystem. Also later is in the next slide. But like H3 is fully supported on Databricks, and that gives you a lot of capabilities. But then there's a lot of like frameworks available ready to use within Databricks and the Spark ecosystem to add support for other types of data types. So probably the most popular is Apache Sedona. It's been like going for many years now. But there's a few others, right? And I'll talk to you a little bit more about it. But all that goes to say that like Databricks is already a pretty solid like infrastructure to do a lot of spatial analysis. I was just talking, and since James have a lot and talk a lot about it, like there's already native support for H3 in Databricks and accelerated by Photon, so it's really fast, really nice. It's only H3, it's not the greatest national grid system, yeah. But I mean, like, yeah. So just check it out. It's a lot of already built in. Now, Carto itself extends on top of what is already available. I like to say that like Carto, it's like what PostGIS is to PostgreSQL, in the sense like we extend Databricks to have full geospatial capabilities inside Databricks, so that you can use it for analytics as a GIS system, et cetera, et cetera. And the way that it works is we've created something we call Carto Analytics Toolbox. It's a set of UDFs that like provide extended capabilities, and under the hood. It uses something, if you don't have Databricks, and especially if you don't have a Spatial SQL, which I will explain in a minute, it will use Apache Sedona under the hood, to add more capabilities. And then, or like it will use a Spatial SQL, which is a faster way, it's Photon accelerated if you are in Databricks and you have a Spatial SQL enabled. And all of this, in Carto essentially means that whatever you do in Carto, it like gets computed and it gets pushed down towards, like the data warehouse. And Spatial SQL, a lot of you might be wondering, what is the Spatial SQL in Databricks? Well, there's the great news. There is a Spatial SQL support in preview on Databricks now, which means that now there's a native geospatial data types on Databricks with I think, sorry, I got it in here, like 58 and counting functions. So that's a pretty big deal. Because finally, it's going to be possible to use Databricks, like natively all the way down, with native geo support. And I think, like that's opening up. At least, we couldn't be more excited. So talk to us about this. Now, the analytics toolbox that I was talking about, like provides you with, like more than 60 more like functions on top of what you have. If you're familiar with things like creation of tile sets for like effective visualization of very large data sets, or routing, or geocoding, or you need, like clustering and so on, we add all those capabilities so that you can leverage it within the ecosystem. Now, why are we doing this? And I want to go a little bit more generic in here. Like the vision that we have at Carto is that like for a long time, geospatial data has been too much like a niche. It's been a silo, and essentially you had to use a specialized software, GIS software, and you have to use a specialized format, GIS data formats, to be able to do spatial analytics, right? And what our goal really is how we can enable this type of like spatial analysis just where you have the rest of your data. And we're calling that the breaking the GIS data silo. And we think that is a very fundamental paradigm to really, in a way, like, cool. in a way, like do your digital transformation of your geospatial kind of like, I mean, like operation inside your organization. So we're very excited about this concept, and we've been working on this now for quite some time. What does this mean? Oh, believe me, my wife just calling me right now. That's all right. So, so what we mean with this is that, we're trying to essentially kind of like make available everything that, like you have on geo, on the geospatial world, available, within the generic kind of like modern data stack. And for that, for example, we've been working now for almost 2 years on GeoParquet, which is a way to kind of like standardize how you represent geospatial data on Parquet so that you can use it natively within Databricks or Spark. So GeoParquet is on version 1.1. It's encoded in well-known binary or GeoArrow. If you're interested in GeoArrow, it's very, very excited also, like advancements going on in there. Just ping us. And we are actually on the process of standardizing it at the at OGC, at the Open Geospatial Consortium. So so it's actually got a lot of momentum. A lot of products, are starting to add support for GeoParquet. And this is a very great way to think about, like how you create your data, your geospatial kind of like data, like how do you can store, like some of those data. So very excited about that. One thing though, that Carto has been adding is right now in their kind of like comments, for everybody, is also how we can represent raster data in this format. So we call that Rasket. I don't know if it's a good name. We still have to kind of think about it. But the idea is rasters in Parquet, right? GeoParquet sounds better. So, but okay. So in Rasket, the idea is like if we can represent rasters as regular Parquet kind of like files, we will be able to, and then in an efficient way, we'll be able to combine vector, raster with any other type of data just using any kind of like Parquet support system, which is very, very big. So, so we have a proposal towards that, and it's actually the way that Carto works internally because we have raster support inside there. And the idea is that it will support multiple projections, it will support different encodings, and it will be multidimensional. So if you're into I'll say like NetCDFs and things like that, this is the idea. We're trying to cover that, right? So for me, it's super exciting because it means opening up a ton of new data to this ecosystem. I'm very excited about that. Now, and of course, with the news and so on, and the whole kind of like drama around Delta and Iceberg and so on, that is definitely the future. So there is a working group already, and if you're interested, tomorrow there's a meetup for GeoParquet, where we'll be discussing a lot of this, to add native support, geospatial native support on Apache Iceberg. So the idea is that then you will be able to kind of like store all your vectors, ideally also rasters, and like in Iceberg, kind of like format, put all the metadata then, and then you will be able to use from any kind of like systems. So the whole benefits that, like the rest of the world is having, like bringing it to the geospatial world. So I like to say that, like somehow, like the geospatial world has always been 4 or 5 years behind the rest of analytics. What we're trying is, to say like, no, let's use the formats that the rest of the world use so that we stay at the same pace of innovation like else. And like Iceberg is an incredible kind of like initiative, like it's going to change how we define our data lakes, and, like having geo support from the beginning is a very big thing. And we call it, like don't make geo a spatial thing. Now, this is actually how it looks a little bit on the raster side. So what you look at in here is a raster. For those, I'm sure most of you know what it is, but like think about like an image where you call like encoding like information in a continuous space, right? So in this case, it's flooding risk. How risk is, the level of risk, of in a particular location. So our goal is to enable use cases like this, where you want to calculate what is the risk of all my portfolio. Imagine that you're an insurance company and you have like hundreds of thousands or millions of buildings that you want to check what is the flooding risk for them. So the idea is that you will be able to store like this flooding risk as a raster, as just one more table, just one more file in Parquet, right? And be able to intersect directly on SQL, like vectors versus raster. And technically, like in a very, very simplified way of thinking it, think about like a raster. Rasters, like you can split them into a pyramid or into tiles. Into tiles first, and each tile of the raster becomes a row on Parquet, right? And then all the pixels within that tile get encoded into some sort of like an array, inside that row, right? So it's in essence that's the idea. It's a little more complex than that. And how you encode, these arrays, there's like multiple ways that you can do it and for different reasons. But at its core, that it is. Now, a 2 gigabytes, something like a 2 gigabytes GeoTIFF, which is a very common raster format, will become around 2.2 gigabytes Rasket, like this, in terms of Parquet. So it's pretty comparable in size. It's probably, you can say that, like some of, cloud optimized GeoTIFFs and certain like specialized geo formats will be better. But by having it this way, it means now raster can live with the rest of all your data without having to use any specialized tools, right? So we think the trade-off and, working on this direction is more important than, just trying to squeeze the last bit of, like performance on a special call, like a spatial format. Wow, so we even got 4 minutes. So I thought, to do a quick demo to show you guys, since we're very excited about like the new support. This is Carto, by the way, when you're getting here. What you see now is that we have, under here, we have a new connection, which is Databricks. And essentially what this will ask you is to use a cluster and a SQL warehouse, right? So once I've connected this, I have here on Data Explorer, I can go here to, I can explore the data on my Unity catalog, so it actually requires a Unity catalog in here. And I have a few tables already available in here. And as you can see here, like some of them are tile sets. Let me see if let me actually open up a few things like this one. So in here, I have a table that essentially is called like an H3 grid. So you see, like this is the table, and you see I'm only have like an H3 column with the H3 ID, which essentially is like an integer, and then I have a bunch of properties associated with it. This is essentially pretty much what James called like, we call it geographic support system, but yeah, this is called like a common pattern in there, right? And you can see like how in Carto, I can zoom in, and you see like how as I zoom in, this is Carto's doing dynamic queries to Databricks using the native spatial, the native H3 support that Databricks has, and you see I'm just getting more resolution. I have other things like if you're familiar with tile sets is a way to call like visualize or pre-process very large tables. So here's I think it's US counties with a lot of definition. As you can see, as I zoom in, like we are like retrieving kind of like more fine-grained geometries as we go in. That's how we can handle like very, very large data sets, right? So that's on the visualization side. I want to show you also a little bit on the workflow side. This is the tool, like I said, like for doing analysis. Yeah, and it goes like this. Sorry, it's maybe it's small. It's a bit hard to demo with a microphone. But yeah, so essentially, kind of like the idea in here is that like you can drag and drop tables, and then so like just kind of like drag a table, and then you have here these components that essentially like match to a spatial SQL capabilities, and you can extend it with your own functions and so on. The idea is just run, and that runs actually on a Databricks cluster. So that's on one side. The last thing I want to show you is on the maps side. I was trying to play with a map before, so let me actually go like, I'm just gonna make a new map. So this is what we call Carto Builder. It's a user interface to design maps like the ones that James probably has been doing. And what I can do in here is actually add things like source. So I'm gonna add here, it's looking at my, and I'm going to add, I'm just gonna add this data set. And yeah. You can see now it's, and here I can go and change things like, like I'm just gonna change this and gonna make it, a little bit more cool, like this. And, like, oh, actually maybe the color I wanna call, I do it based on, I don't know, it's right now, actually just pretty much doing it a little bit random in here. Just gonna remove, I choose the stroke color. Yeah, sorry, no, I'm gonna do the fill color. I'm going to change this to something like this, and you get something like that. And then, but I want to call like maybe do it a little bit more like that. So you get the idea, right? And I can call like check the height, and I can do it based on something like the area. And I'm going to go like 3D, and going to make it a little bit more like this, so that it's more extreme like that. You get the idea. I can display it. You get the concept, right? So this is the idea of how you make like what I'm saying. And under the hood, what this is all doing is just firing queries to the Databricks warehouse to kind of like get the data as we go dramatically. So that way you can handle like 50 megabytes or like or 100 megabytes kind of like data set, or like gigabytes or like terabytes. I mean, like essentially it's just kind of like loading the data progressively. So with this, I think we already finished. So that's all what we have for today. We have like I said, we have a booth here today. Tomorrow there's a Geo Parquet meetup. If you're interested, just let us know, and we'll be happy to answer any questions. Thank you.